So we defined the sea, where the storm is churning the ocean and sending off waves towards the beach, where you may be peacefully sitting and not be even seeing the storm, right? So what is the storm doing? Basically, it's putting energy into the ocean, right? And we already said that the amount of energy that gets from the winds into the ocean is only about 2%. We talked about it in the context of currents, where steady winds are constantly dragging the ocean. Here we are talking about a storm, which is not a steady wind. It starts and it dies. So it's putting energy into the ocean, and that energy is being radiated away from the region where the sea is, or the region where the waves are being formed. As we said, waves always carry the energy, right? So what determines the wave energy? Obviously, it's the wind speed, how strong the winds are, and the duration, how long the wind is brewing, how long the storm persists, right? And what's called fetch, how large the storm is. If it's just a little storm, it may not do much, but if it's a large storm, even if the wind speeds are not that great, if it's large and it's blowing steady winds, you can put a lot of energy into the ocean. So that fetch is the distance over which the energy winds are blowing. So here is a cartoon of it. The storm is happening here. Storms are basically moving systems typically. So here is the wind that is steering the storm. The storm is still, remember the trade winds, westerlies, etc. are still there. Storm is acting within the system. So those winds can steer the storm in different directions, like the hurricanes move, the cyclones move, and so on, right? But here the storm themselves have winds associated with them. There is, as we saw in the hurricanes, they may be driven by the evaporation and condensation heating, or in the mid-latitudes they may be driven by energy that is being put in from the jet stream. Remember we said jet stream is a westerly, surface winds are westerly, so momentum can come down and so on and so forth. So here is the ocean storm brewing. The limits of the storm are shown by this red dashed line. So that's the fetch, or the length over which the winds are blowing, and there are several wavelengths being generated by the storm. Storm is typically not steady. It's blowing in bursts, so it's producing different wavelengths. Okay, and we said the wave celerity is wavelength divided by the period, right? Period is an intrinsic quantity related to the wind forcing. So longer the wavelength, typically faster the speed. So if a wave is fast, it tends to move faster than the storm, and it gets away from the storm and then leaves the storm area and keeps traveling far away, all the way to the beach where you are sitting, before it hits the bottom and becomes a shallow water wave, and so on. So swell is basically this nicely sorted out waveform that peacefully keeps traveling along, as long as there's no friction damping it, and so on. So it's carrying this energy to far away from where the storm is. So wave height is a direct indicator of how much wave energy is being carried. So wave height is usually less than 2 meters. We will see that in some places. You can imagine where. So wave heights can get much higher. And we will also see what rogue waves are, where some constructive interference happens and you can get tens of meters of wave heights and so on. As they approach the atolls, however we pronounce it, coral reefs or whatever, islands, hidden volcanic sea pillars or whatever, or land, then the waves begin to hit the bottom, and then breakers called whitecaps form when wave height reaches the critical steepness of h over L equal greater than 1/7 that we just saw. Okay, and there is a Beaufort wind scale, English Navy captain, after which this scale is defined. It describes the appearance of the sea surface. So if you're a sailor and out in the middle of the ocean where there is no clear reference, despite the GPS you know where you are, you need to monitor the horizon all the time for how the ocean looks. Whether it's getting choppy, whether there is a storm that's sending big waves, and so on and so forth. You've probably seen a movie called The Perfect Storm, which is based on a real life situation off of northeast US, where many storms combined to form this huge waves that toppled many fishing boats and killed many fishermen, and so on and so forth. So we'll look at a Beaufort scale, which relates to the wind speed later on. Obviously, that relates also to the wave state, or the sea surface state, or the sea state. Okay, the altimeter that we talked about before, that measures the sea surface height, obviously can be used to measure average wave heights. And you can see here that the North Atlantic and the North Pacific are stormy regions with wave heights of the order of 2 to 3 meters. Most of the tropical oceans are calmer, as we know. They are the doldrums and so on. So the trade wind regions pick up in wave heights. The tropics remain, whereas the Indian Ocean has a different structure because the southeasterly trades in the southern Indian Ocean, because it's a small ocean, can blow stronger waves and so on. And the Southern Ocean, it's a channel, so a wind can put in much more than this 2% energy that we talked about for these other oceans, where the boundaries make it harder because the fetch gets limited. Remember, wind speed, duration, and fetch. The fetch gets limited by the wave coasts, the ocean coasts on either side, whereas the Southern Ocean has no coast, so you get much more energy going into the ocean, which means much more wave energy, so wave heights will be larger. So you can see here you get waves of greater than 6 meters in the Southern Ocean, which actually prevents people going to observe this ocean, going to Antarctica in the winter months. Winter months, as we'll see later on, tends to be stormier than summer months, even at high latitudes. So winds during the winter tends to be stronger. The Southern Ocean is has strong winds anyway. It's known as the screaming 40s, roaring 40s, furious 50s, and screaming 60s. So 40-degree latitude, 50-degree latitude, 60-degree latitude, it gets so strong that even big ships cannot go there. Which means what? The ocean data tends to be collected mostly in the summer months. So you have a bias in the data that is collected. There is a lot of data being collected, but if it's being collected in one season because of storms, then obviously you have much less information about the winter months than the summer months, right? So again, you have to connect all your concepts in every context. Here we are trying to bring the seasonality of the winds into the wave dynamics that we are talking about. Okay.